If we were to graph out this process of forming high-energy products from low-energy reactants in a potential energy diagram, it would look like this. The potential energy increases from reactants to products. Notice that there's no specific x-axis. The delta E is the change in chemical potential energy between the reactants and products. Likewise, if we were to compare the potential energy diagram of photosynthesis to cellular respiration, it would look like this. The net difference in energy is represented by the delta E. I say net difference because if I was to graphically illustrate a more complete representation of the changes in chemical potential energy as we go from reactants to products, it would look like this. It turns out that energy is required to break the bonds in the first place, frequently called the activation energy. In high school chemistry, we show as distinct steps the decomposition reaction as the reactants form elements, and then the formation reaction as those elements form the products. Your book illustrates this as energy being applied to molecules and then breaking to form atoms. This is an endothermic process. Energy is required for the reaction to work. It's worth noting that in biological systems, the energy required to break apart glucose in cellular respiration is less than other hydrocarbon combustion reactions. Enzymes cause the reaction to occur without all the activation energy usually required. This is why liquid water is a product of biological combustion and not steam, because the enzymes act as catalysts, causing the reaction to happen at lower temperatures. We will talk more about this later in the unit. The separate atoms coming together to form bonds create molecules releasing energy. This is an exothermic process, and energy is released into the surroundings. If the energy required to decompose the reactants into elements is less than the energy released to form the products, then the overall reaction is exothermic. The change in chemical potential energy in an exothermic reaction would show up as a negative value. If the energy required to decompose the reactants into elements is more than the energy released to form the products, then the overall reaction is endothermic. The change in chemical potential energy in an endothermic reaction would show up as a positive value. Energy and enthalpy. The total amount of energy in a system can include all the types of potential energy, including chemical energy and the energy involved in phase changes, as well as kinetic energy. It is impossible to determine the total energy of a system. However, chemists have determined that the enthalpy of a system is related to its total energy, and a change in the enthalpy of a system is equal to the heat absorbed or released by the system. The enthalpy of simple decomposition, where a compound reactant produces elemental products, is the total amount of energy involved in breaking the intramolecular bonds between the atoms of a compound or molecule to reveal only elements. The enthalpy of formation, where element reactants come together to form a molecule or compound product, involves the total amount of energy involved in creating new intramolecular bonds between the elements. The enthalpy change of a reaction is the difference between the energies absorbed from the surroundings to decompose the compound into elements, and the energies released back into the surroundings as these elements combine to form different compound products. Enthalpy change is a measure of relative enthalpy. It's like saying that the distance between 2 points is 10 centimeters, without any indication as to where either of the 2 points actually are, other than 10 centimeters apart from each other.